Hello everyone. In this video, I want to talk about the second really important question or problem in calculus, which is how do we find the area under the graph of a function? So what I'd like to do in this video is provide just a little bit of introduction so we know the general process as to how to do this. So to start off with, let's say that we have a function f of x and we want to find the area underneath that function in between some interval, and let's say that interval is from a to b, and then the region, the area that we want to find, is going to be bounded by the line x equals a, the line x equals b, the two ends of our interval, the curve of our function, and the x-axis. So the region that we want to find the area of is this one right here. Now, because we're dealing with a curve, we may not necessarily have an equation or a formula that we can use to find the area of this. It may be a goofy shape that we can't directly find the area of. Well, that's where calculus is going to come in. Furthermore, we also want to come up with a process that will work for any function, regardless of what it looks like. So the way that we do this, we're going to go back to use something that we do know how to find the area of, which is rectangles. So what I can do is I can take this region from A to B, and I can split this up into a bunch of different rectangles. I know that the area of a rectangle is its width times its height. So if I fill in this region as best I can with a bunch of rectangles, like so, what I'm going to end up with is not necessarily the exact area, but I am going to end up with something that is very close to the area of this region. So as you can see, if I fill this up with rectangles, I do have a little bit of error. I have a couple of regions here where we are missing some area, or I could draw the rectangles a little bit bigger where I'd have some extra area on the other side of this function. Well, the idea is the more rectangles I use, the closer I can get this to being the actual area of the region I want. And then we can use calculus to say, what if I let the number of rectangles become unbounded? So in other words, what if the number of rectangles approaches infinity? Well, if we can do that, we can come up with the exact area underneath the curve. So to make sense of that a little bit more, I want to go through a very simple example. So the example here says approximate the area of the region enclosed by the graph of y is equal to 1/2 x plus 3, the x-axis, and the lines x equals 2 and x equals 4. So why don't we just start by graphing this and taking a look at what our function looks like. So we have 1/2 x plus 3, which is just going to be a line, and we're looking at the interval from 2 to 4. So if we mark off an interval here, and then our line, we have a y-intercept of positive 3, and we have a slope of 1/2. So drawing in a couple extra points. And then the interval we're looking at is from 2 to 4. So let me draw in the line, and I'll also draw in some vertical lines to represent our interval. All right, so in blue, this is our line, y is equal to 1/2 x plus 3. And then I have the vertical lines, x is equal to 2 and x is equal to 4. And the region that we want to find the area of is this region in between all of those lines and the x-axis. Now, taking a look at this one, this is a trapezoid. So we do have a way to find the area of a trapezoid. The formula for area of a trapezoid is 1/2 base 1 plus base 2 times the height of the trapezoid. So in this case, we can actually just find the exact area by using a formula. And why don't we do that so as we start to build our calculus process, we can compare to what the exact area is. So on the line, so if I take a look at where this point is at x is equal to 2, We have 1/2 times 2 is 1, plus 3, so this is at the point 2, 4. And then at the other end of our interval at 4, we have 1/2 times 4 plus 3, so that's going to be 5. So this is at the point 4, 5. So the two bases of this trapezoid, we have a length of 4 and a length of 5. And then the height in between those two bases, we have a distance of 2. So the area, 1/2, 4 plus 5 times 2. So our total area is going to be 9. So that's the exact area. But like I said, a lot of times the functions we're dealing with are not going to be straight lines, and we're not going to have a formula that will allow us to find the area. So that's where these rectangles come in. So why don't we start by building that up, and we're just going to start by taking a look at one rectangle within this interval. Now when we pick out these rectangles, we actually have two options. So again, we're looking at the interval from 2 to 4. And the two options that I have to do my rectangles is I can take a look at the rectangle that goes to the leftmost side of my interval, or I can take a look at the one that goes to the rightmost side. So within this interval, the leftmost point is at x equals 2. So the height of the rectangle I'm going to use is going to be the point that's on this function at x is equal to 2. So we're focusing on the leftmost. Now the other option we have is if I go from 2 to 4 again, and now instead of using the leftmost point, we can take a look at the rightmost point. So in this case, that's going to be at 4. Now if I draw in these rectangles, so the height of the rectangle with the leftmost is going to be at the point x is equal to 2, so this rectangle is going to have a height of 4. If we draw in this rectangle, we can see that this is going to be an underestimation. We have some region left that we're not accounting for. If I go to the rightmost point at x is equal to 4, now this rectangle is going to have a height of 5. And if I draw that in, you can see that this is an overestimation. So the rectangle goes above where our function is. Well, we do know how to find the area of a rectangle, so let's see what these areas are. So for this first one, we have area. It's going to be the height times the width. So our area, the height here we said was 4, and we have a width of 4 minus 2, which is 2, so the difference in between here. So 4 times 2, we have an area of 8. In our second rectangle, we said this has a height of 5. And this has the same width of 2, so area is going to be 5 times 2, so this is an area of 10. Now one of these is an underestimation and one of them is an overestimation, but what that leads us to is we can conclude that the actual area has to be somewhere in between 8 and 10, which we know it is because we already found the exact area. So this is just an approximation. And this was just using one rectangle. Now, if I use more rectangles, I can get an even better approximation. So why don't we double the number of rectangles we use, and let's go up to using 2 rectangles. So we're going to look at the same interval from 2 to 4, and we're going to do the same thing. We have 2 options. We can use the leftmost points, or we can use the rightmost points. But in this case, we're going to take our interval from 2 to 4, and we're going to split it up into the interval from 2 to 3 and the interval from 3 to 4. So 2, 3, and 4 here as well. So if I just write that out, we have the interval from 2 to 3 and the interval from 3 to 4. So now using the leftmost points, within this first interval from 2 to 3, we want to use a height at the point x is equal to 2. And then for our second interval from 3 to 4, we're going to use a height at the point x is equal to 3. If we use the rightmost points, for the first one, the rightmost point is going to be at x is equal to 3. And for the second interval, the rightmost will be at x is equal to 4. All right, now let's draw in these rectangles. So using the leftmost points, so our first rectangle is going to have a height at x is equal to 2, so that's a height of 4, just like we saw when we're using one rectangle. And then our second one is going to have a height at 3, which I believe this is going to have a height of 9 over 2. And now for our second, using the rightmost points, so the rightmost in the first interval, this is a height of 9 over 2. So here's the first rectangle. And then our second rectangle, the rightmost point is at x is equal to 4, so this one has a height of 5. Now, same idea as the last one. When we use these leftmost points, we do have an underestimation, so we have some area that's missing. And when we use the rightmost points, we have some extra area, so this is an overestimation. Now let's take a look to see what our area ends up being. So using the leftmost points, the width of both of these rectangles is 1. So this first one has a height of 4, and our second rectangle has a height of 9 over 2. So the area of the first rectangle is 1 times 4. And if I add the area of the second rectangle, we have 1 times 9 over 2. So this is going to give me a total area of 8.5. And if I take a look at our second one using the rightmost points, these also have a width of 1. Our first rectangle has a height of 9 over 2. Our second one has a height of 5. So we have 1 times 9 over 2, the area of the first rectangle, plus 1 times 5, giving me a total area of 9.5. Again, these are approximations, but what we can conclude is that the actual area has to be somewhere in between 8.5 and 9.5. So comparing that to when we were just using one rectangle, the approximation is getting closer. We know that the actual area is 9, which is right in the middle of this interval, but hopefully, as you can see, the more rectangles we add, the closer and closer this approximation is getting to that actual area. Now, if I was to take this interval from 2 to 4, and I was able to split it up into an infinite number of subintervals and draw in an infinite number of rectangles, that approximation would be getting very, very close to the actual area. So what that means is if I can use the limit, a calculus idea, if I can use the limit as the number of rectangles approaches infinity, and I can find the limit, that should give me the actual area of the region.